Hello, students. We've got Chapter 5 review questions that came in, and there were a number of them here. So let's tackle some of these and kind of see how we do. The Dead Sea. So we had question 12, 20, 21, 23, 24, 20, 35, 41, 42, 43. So quite a few, but we'll tackle them as we go. So we've got question 12 is the first one, and we've got the Dead Sea's elevation is negative 1410. Wow. 1,410 feet below sea level. If the Dead Sea is this many feet less than Mount Everest, how tall is Mount Everest? Well, let's use that. Let's see if we can get there. Okay, Dead Sea is this many feet less than Mount Everest. So again, I don't know how many feet tall Mount Everest is, but what I could do is create a nice little expression that would say, here's Mount Everest. And if I take 30,439 feet less than that, that will give me the Dead Sea's elevation. So this is what I would write out as an expression. And then I could add to both sides to solve that equation. So really, when you look at this expression, I have a negative number added to a positive number. Because the signs are different, I would be calculating the difference between the two numbers, doing subtraction. And so off to the side, I could just do 30,439 minus 1410. The sign would be with the larger absolute value, in this case positive. And so 2, 0, and there we are. So 29,029 would be the height of Mount Everest. So there we go. All right, we'll move on to the next one. Make sure that I'm answering these questions. All right, so there we go. So we're on track. Let me delete those and we'll move on. The next question was 20. D as in dog. This one right here. So it's factor and simplify. So this utilizes, number 20 utilizes a technique that we're introduced to, or at least reminded of, I guess would be really a better way to think about that. This does come from your prerequisite courses in algebra. And the idea is that I take a quantity squared minus quantity squared, and that is equal to, as long as they're both squared, I get this one minus and this one plus. And what you can see is if you do distribute, the reason why this is true is you distribute and you get cloud squared. Then you get cloud times box. Then you subtract a cloud times box. So those kind of cancel each other out. And then you have minus box times box, which is minus box squared. So that's why it works. Okay. So if you were looking at like part C and you had x squared minus 36, what you want to do is think of what thing is being squared. So you may want to rewrite this as x squared minus 6 squared, and then you get x minus 6 and x plus 6. Boom, shakalaka. Now let's try the next one. 81 y to the fourth minus 16 x to the fourth. Looks more complicated, but I'm going to go right back to this. And the thought process is just think, what is being squared? So something is being squared minus something is being squared. So what squared gives me 81? 9. And what squared gives me y to the fourth? Y squared. So I can do that, and then over here do the same thing. I get 4x squared. And so now I just use that. Again, think of these as like a cloud and a box. So I have 9y squared minus 4x squared in parentheses times 9y squared plus 4y squared. That is exactly what we saw right up here on the top. Now, the only thing to think about is, could I factor again? Do I have another one of these? And I'll change color. We'll go with orange. I wonder if there's another thing that looks like something squared minus something squared. And yeah, there is. So what I really have here off to the side is I have 9y squared minus 4x squared, which is the same thing as thinking of 3y quantity squared minus 2x quantity squared. And that would be my cloud and box. So what I end up with is 3y minus 2x times 3y plus 2x, and then just bring down the other chunk that we couldn't break down any further. And there you go. So a little bit further on this one, we had to go one extra step. Again, hopefully that gives you the concept. Now, how does this relate to the number pieces? Well, picture in your mind if somebody had, let's say, 27, and they're trying to prime factor it, right? And they say, oh, I can factor it into 9 times 3. And then they might say, okay, so I'm done. But you have to be able to look and say, well, wait a minute, 9 is not completely factored. We could go kind of factor that again. We could go again with the same process. And that's what happened here with this first piece. It turns out that that first piece, even though it was part of a factorization, it wasn't completely factored. And so that's what we would do if we wanted to break it down a little bit more. Very cool. That is 20 part D. Next up, clear all my drawings. And I've got 21 part C. It looks like, yeah, 21C. Okay, so 21C, let's take a look, get a little white space in here. 21C, classify as true or false. Well, let's give it a chance. Let's see how they do. Just there it is, 21. 21C, okay, so C, this says for all integers A and B, if A is less than the opposite of B, then A is less than 0. So A has to be less. You heard what I said. I said the opposite of B. If you said the word negative here, then you probably answered this question in one particular way, but it does not say that B is negative. This symbol can represent the opposite of B. So yes, if B was a negative number, then the opposite of B would be positive. So if I was answering this for all integers, then what do we have? So to me, I would have to say that this one is false because I can come up with a counter example. And so if you have a counter example, let's see here, right? I would say, okay, so B, let's say B is equal to -5 and A is equal to 3. Then let's check it. A, which is 3, is less than the opposite of -5. That is true. So I've found a case where A is less than the opposite of B, but they said A has to be less than 0, and I did not find that to be the case. I found A to be positive. So I found a counterexample, and once you find a counterexample, the statement itself can not ever be listed as like a theorem. We would have to say that is not always true. Okay. How could we have made that true? Great question. So if we said A is any integer and B is any natural number. See, that's different than what's here. It says all integers A and B. If A is an integer but B is a natural number, then guess what? The opposite of B, which is a natural number, right, has to be less than 0. Okay. And we know that A is already less than the opposite of B, which means A would have to be less than 0. So that's one way to kind of make it work out, is you just kind of fix the number and say the number has to be the kind of number that I'm looking for. All right, so that takes care of 21C. What else do we have here? 23C. Okay, 23 parts C. Use the chip model to illustrate. Oh, yeah, this is a great one. Okay, so we got to be thinking back to what we either did in class, what you put in your notes, what's in the textbook. But the idea here is I'm multiplying If I was multiplying like in part A with a positive, I would think of this as put in. So I would put in 5 groups of -5. But here I'm not putting in, so I need to take out 2 groups of -3. I need to take them out. But what am I taking them out from? I'm taking them out from nothing. I'm taking them out from nothing. I start with nothing in here. I start with 0 in here. And so what I do is I make some pairs. So I have black, 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 black. Again, these are 0 pairs. So I'm mixing up some black chips and some red chips, just like we did in class. So right here, this has a value of 0. Okay. If I was putting things in, I would start with 0 and I would put them in. The arrows would be showing going in. Here, I need to take them out. And if I am taking them out, then I need to take out 2 groups of -3. So I find a group of -3 and I demonstrate that going away. I remove another group of -3 and there they are. So I took out 2 groups of -3. My final result is, and I'll switch back to black, which is +6. So my answer would be +6, and -2 times -3 is +6. All right, rocking and rolling. That was 23. Let's move on. We've got 24 and then a couple more at the end. Let's take a look. Whew, 24. The following state temperatures are given at the top of the next page. At the top of the next page? Whoops. How about right below the question? Good job, proofreader. Order the given states according to their lowest temperature from lowest to highest. Okay. So now we do have to think about this. What does it mean to be a low negative temperature, right? So we need to think about what does it mean to be less than? So I'm going to review that. Less than, okay? So A is less than B if and only if there exists a natural number. This is the key part here. A natural number. That indicates right away it can't be 0 and it can't be negative. It has to be a natural number, C, so that A plus C is equal to B. So that's what it means to be less than. So if you had these two temperatures like -33 and -40, take a look, -40, I could add the number 7, +7, and I would end up at -33. And you could visualize this, or you could do it with the chips. Take -40, which would be 40 40 red chips, and I'd add 7 black chips to it. I'd make some 0 pairs, and poof, there went away some of your negatives, and I end up with -33. What does that tell me? That tells me that -40 is less than -33. So if I want to go from lowest to highest, -40 is lower. But I could look on this list and I could find the absolute lowest, and Oregon as the absolute lowest, -48. Right after that, -46. Right after that, -44. Right after that, -43, -40. See what I'm doing? Just going in order, because the larger the absolute value of a negative number, the smaller the actual value. Okay. So there we go. That is a question similar to 24. Let me make sure that I answered the student was looking for correctly. How do I explain to a student? So this is one way to explain. It's the definition of less than. What does it mean to be less than? If you're looking for a number line approach, here's 0, here's 5, here's -2. And you could say, well, look, numbers this way are larger. So this is more of a, depending on how young the class is, if they're getting into negatives, they should be just fine with the idea of the definition of less than. But there it is. So you want larger numbers are to the right. Where would -40 be? Right? And so if you think about that, here's -33, here's -40 because it's 40 steps in the negative direction. So you could look at this and say negative 33 is more right on the number line, which would mean negative 33 is larger. Okay, so two different approaches. One's a number line approach. The other is the definition of less than. And yeah, I prefer, and once you get used to math, you start realizing those definitions are really important. So you kind of start gravitating towards the definition. If a student says, is this a function? You should start asking them, what's the definition of a function? Is this completely factored? Is this in simplest form? What does it mean to be in simplest form? What's the definition of simplest form? So yeah, that's kind of the approach that I take. Let's see here, 35 was one. Find integer solutions to the following pairs of inequalities. Ah, yes. So this is an and statement, and going back, this is good. We're brushing up on these pieces. We're going all the way back to chapter 2. In chapter 2, we had statements that were written as and statements. So I'm going to cover some of them up. I'll do a couple others. I'm not going to do all parts of this one, but we'll get you going on the right track. What is the idea? The idea of an and statement is, think about the word and. Think about what it meant. And both must be true. We saw this with and statements, right? Each one is a statement. In order for the and statement to be true, both had to be true. So when you see negative 2x is less than 14 and you solve that and you reply with, aha, I know what values work. Let's come down to the number line. Okay. Oops, I'll just do a horizontal number line. I was going to do an x and a y, but I don't think I even need to here. So I'm going to go, here's 0, 2, 3, 4, 5, 6, 7. There's negative 7. Okay. And notice this says I want all the x values. X's need to be greater than negative 7. So I am going to shade the region of those. Let me see here. Do I have a highlighter? Oh, I do have a highlighter tool. Okay, I'm using the highlighter tool. There we go. Okay, so here's what I want to do. I'm going to shade everything that goes from negative 7 this direction. Okay. There's that part. Okay. Well, let's come back up here. Let's do the next component, right? Let's do the next component. And I'll choose a different color so that we can kind of match them up. This one says 3x is greater than negative 15, which means x has to be greater than negative 5. Okay. So I'm going to color that one in on the number line too. Okay, ooh, let me first put negative 5. There's negative, oops, that was too, I was still using some kind of highlighter or something. Okay, here's negative 5 right there. Okay, and so I want to go this direction. So from negative 5, I want to go this direction. Everything has to go that direction. Okay, and now let's go back to what the question added in between. It said, oops, well, too thick again. Sorry about that. It said and both of them must be true. Okay. So see these numbers down here where it worked for the red piece, but not the blue piece? Sorry, those don't work for both. The numbers that work for both, if I did one in red and one in blue and I shaded that way, would be the numbers that are in purple. Purple, like I've colored here, is the and. It's the overlap. It's where do they both meet up. So you can see, aha, even though there's a little tail down here, it only works for one, so I have to remove it. My final answer would be all numbers that are greater than negative 5. That's where the overlap starts. Okay, so if you were doing this with other questions, okay, just so you're kind of on the same page, you might see one where one group shades this direction and another shades this direction. Okay. Now, if you're looking for where is the word and, the and is where do these overlap? Now, yellow and blue make green. So this portion is the and portion. if this question came back and didn't use and, if it used the word or, then you could be in any one of them. So you could be yellow, blue, or green. And in this case, if it was or, it would be anything on those two directions. So that's the idea. Very similar to the Venn diagrams, right? The or statement, you could be an A or B or both. You had to be in at least one. But for the and statement, you have to be in the overlap, which is where they intersect. Okay. There we go. Let's see here. I think that's probably about it. But maybe I'll talk briefly about, because there's an absolute value here and some square root pieces. So let me do just a brief interlude on those. Okay, so for a problem where you have x squared is less than 9, I know you want to take the square root. I get it. I feel you. The square root of x squared is less than the square root of 9. The square root of 9 is 3. But the issue that sometimes comes up with students is here. When you take the square root of x squared, perhaps your gut is telling you it's just x. Well, it's not though, is it? Because x could have been a negative number that I squared and got a positive, and then I take the square root. So what I need to do is I need to say, I don't know whether it's positive or negative. I need to include the absolute value. So the square root of x squared is actually the absolute value of x. And when you have the absolute value, that is the distance to 0, as we talked about. So if you were sitting here, here's 0, and you want the distance to 0 to be less than 3, you could come out and say, well, here's 3, and there's negative 3, and I want the distance to be 0 to be less than 3. Well, then I need all of this. I don't need that part, so I'll put a circle around it. Don't include that part, but everything else, all this stuff in the middle, everything here. And that would be the answer to the first part. Shaded region, not including 3 and negative 3, because if you plug those in, they're not less than 9. They'd be equal to 9. Okay? And similarly, you could do the same thing here. So if you have absolute values, think about what it means. It means a distance. If the distance is less than something, then you are standing here, and the distance is within reach. It's within 3 units of reach. If the absolute value is greater than some number, greater than would be kind of those outer pieces. They're further away. And also, at least for part C, be thinking. Absolute value, think about it. Can it ever be negative? That would be my nudge for part C. So that's 35. We'll jump down now to the next question the student had, which is question 41. We had 41, 42, and 43. Okay. So 41, let's check. 41, find the missing terms, arithmetic, geometric, or Fibonacci type. Okay. So, doop, 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 doop. Well, let's see here. It says it's arithmetic, geometric, or Fibonacci. So if I go -1, comma 1, comma blank, and if it's geometric, then there has to be a common ratio, and that ratio would have to be -1. -1 times -1 gives me 1. -1 times 1, so if I keep going where I multiply by -1, I should get -1 back. But according to the list up here, I get 0. Okay, so part A, it's not geometric. Let's try arithmetic. If it was arithmetic, then I would add the same thing to both sides. So I must have added 2, and then I must add 2 because it's going to keep going. So my next number should be 3. My next number is not 3, it's 0. That tells you it's not arithmetic. There's only one option left, and it's the Fibonacci type sequence. And in the Fibonacci sequence that we talked about much earlier, maybe back in chapter 1, what we did is we added the 2 terms to get the next term. Then you add these 2 terms to get your next term, and it continues on like that. So -1, 1, -1 plus 1 would be 0. 0 plus 1 would be 1, right? 0 plus 1 would be 1, and 1 plus 1 would be 2, and finally 1 plus 2 would be 3. So if I needed to find the missing sequence, looks like I'm missing 3 terms. It would be a 1, a 1, and a 2. Then it says find the sum of each of the finite sequences. Well, these are finite, so really all it's asking you to just add these numbers up. It's not asking you to do it in general. The general sum of a Fibonacci sequence is, honestly, it's pretty cool, but it's way beyond the scope of this class. So let's call that what it is. It's just just add all these numbers up. Yeah, so I think one of these is, I think this part B is geometric because I multiply by -2, then multiply by -2. So all you do is write out your list of terms and then add them up. That's all they're asking you to do. Is there a way to find the sum of a geometric sequence? There is, but I'm not going to ask you to know the general case for that. That is actually beyond the scope of the class. It's cool, but not required. So if there is a sum of a geometric, it would be a finite sequence that we'd be dealing with. Okay, which means a fixed number of terms. And then you would just find the values and add them up. That would be how that works for that one. So that takes care of 41 and 42. And then 43, how many missing terms does the ellipsis represent? Oh, how many missing terms? Okay, so be careful on the wording on this one. It doesn't ask you how many terms are in the sequence. It says how many terms are missing because of the ellipsis. So definitely need to know the number of terms. In this case, part A, we could think of this as arithmetic. And arithmetic with a common difference of -2. So any term in the sequence I could write as the first term plus some number of -2s. And we could distribute now. So 101 minus 2n plus 2, which if you go back to what Brooke would do, she would have gone to one term before this and she would have said 103 minus 2n. And there it is. That was Brooke's technique back from chapter 1. Okay, so now all you have to do is say this is the last term in the sequence and plug that in for negative 103 for an. So here's negative 103 is what I would put in. And then you can try to get 2n by itself. So many different ways to do this. I guess I'll just take away the 103 on both sides. And that leaves me with negative 2n and a negative 206, and then divide by -2 on both sides. So n is 103. So there are 103 terms in this sequence, but that's not what the question asked for. The question asked for how many missing terms. So if I know there's 103 terms in the sequence, and I know there's 1, 2, 3, 4, 5 terms that are shown, then the number of missing terms, missing would be 103 minus 5, which is 98. So the ellipsis represents 98 missing terms. And there we go. So that's it. If you are looking at that geometric sequence, don't freak out too much. The geometric sequence is factoring. You know you have to multiply. In this case, you're multiplying by 5 over and over and over again, right? So just keep dividing this number by 5 until you figure out how many 5s are in it. That's your prime factorization. And then you could say, well, how many multiplications did I get to that stage? And I think that should help you along the way. It doesn't hurt to write a sequence like that in prime factored form. So 5, then minus 5 squared or negative 5 squared, then 5 cubed, then ... Notice it's also the same as you can kind of say my common ratio there would be -5. Multiply by -5 to move to the next term. And that would help you get how many total terms there are. Phew, a good set of questions there. So thank you very much to the students for asking your questions. Really hope this gave you what you need going forward. That's it for me for now. Off you go.